My name is ZHANG Rong from the Department of MSE, and my supervisor is Professor ZHANG. It's my honor to be here and have this presentation. And the topic of my presentation today is about the link-based batteries for simultaneously pollutants converting to ammonia and electricity generation. Here I highlight the importance of ammonia at first. Ammonia is an important chemicals in the world, and it's not only the crucial precursor for fertilizer production in the agriculture, it's also a carbon-free energy storage material due to its high energy density, high weight fraction of hydrogen, and the ease of liquefaction. Its decomposition will produce hydrogen energy, which can be used in fuel cell vehicles and the hydrogen power generation. In addition, ammonia can also be directly used in power generation, like the ammonium-fueled solid oxide fuel cells and others. So ammonia is so important, and its demand is increasing year by year, and the demand is very huge. The traditional way for ammonia synthesis is the Haber-Bosch process with the reaction of nitrogen gas and hydrogen gas under very high temperature and pressure. In addition, catalysts like iron or ruthenium catalyst is essential in this process to accelerate the reaction kinetics. Here shows the details of the Haber-Bosch process, where hydrogen is produced from the natural gas. Following several steps like purification and reforming, in the second reforming step, air is introduced to provide the nitrogen, and after separation, they react to produce ammonia finally. This technique is well established for ammonia synthesis and can produce almost half of ammonia in the world. And it makes full use of the useless nitrogen in the air. However, it still has some limitations. For example, it involves the use of natural gas or fuel cell or fuel fossil. So it's involves a large amount of CO2 emission, and the harsh operation conditions like the temperature and the pressure make this process very energy intensive. In addition, the reaction between the nitrogen.
May I make a suggestion? Right? Can you stand up a little bit and just point to the screen? Okay? Because we don't really know what you're talking about. Which part are you talking about?
Okay.
You know how to use it? Yeah. So you use the point. Yeah.
This reaction is reversible, and the efficiency to produce ammonia is as low as 15%. So in this regard, it's highly desired to develop a more sustainable approach for ammonia synthesis. Unfortunately, in recent years, electrochemical synthesis of ammonia has been developed, and here shows its configuration. With two chambers is separated by a membrane to prevent the ammonia migration from the cathode chamber to anode. And in the cathode chamber, the nitrogen is introduced to the electrolyte, which is generally aqueous solution, and then it's diffused on the surface of the catalyst electrode and reduced to ammonia. This approach is as you can see, it's very clean and has no carbon emission. It uses water as a protein source, so it's very great and sustainable. But it still have some limitations. First is it has a very low solubility and yield. The maximum FE reported in recent work is no more than 50%, and the partial current is less than 1 million per centimeter square. There are several factors. First is the competing reaction, hydrogen evolution reaction, named as HER, and its potential is very close to the nitrogen reduction. And there are also other factors like the intrinsic property of nitrogen molecules itself and its ultra low solubility in water. So it's widely agreed that it's very difficult to realize the high yield ammonia synthesis, and it's highly relies on the rational design of electrocatalysts. So many research have paid their attention on developing other nitrogen-containing alternatives to realize the large yield ammonia synthesis. From this global nitrogen cycle, we can find that in addition to nitrogen, there are many other nitrogen species, nitrogen-containing species like nitric oxide, nitrate and nitrate ions. They exist in wastewater or the exhausted gas, and they are harmful to the health of human beings and animals. So if we can transfer this species to ammonia, we can not only accelerate the global nitrogen cycling to balance the ecosystem, but also purify the environment. Here we comparison several stable natural species in terms of their standard potential and their solubility, which are two important criteria for high yield ammonia synthesis. First is their potential, and we can find that compared with nitrogen, the nitric oxide and other two species have very positive standard potential. It means they are much easier to be reduced to ammonia, and nitrate salt has much higher solubility in water. It concludes that these two species are very promising alternative to nitrogen to produce ammonia. Actually, many reworks have been reported to produce ammonia using an electrochemical approach, which is reduced over a catalyst electrode, which is very crucial for the selective ammonia synthesis, because the reactions are multi-electron transfer process, and many byproducts may be produced during this process, and the catalyst is very important. The produced ammonia can be treated by several steps, and finally up to the ammonia chloride and concentrated ammonia solution finally. In addition, in the traditional electrochemical cell, the anodic reaction is equipped by an oxygen evolution reaction, which has a higher potential of 1 to 3 volts. So it means this system is energy input and unit needs a voltage larger than 1 volt. If considering the low potential of zinc metal, and if we can replace the anodic oxygen evolution reaction with a zinc anode, this system can change from the energy input from the energy input to energy output. So in this, devoted in this direction, I'd like to introduce one of our piece, one piece of our work in this direction. First, we prepared a carbon-doped cobalt oxide hollow tube as a catalyst for nitrate reduction, and we prepared this catalyst through the through the tetrastatic conversion of its precursor oxalate doped cobalt oxalate. And we prepared the precursor with the excess oxalate ions by thermal hydroreaction. And after the PVP coating, during the calcination process, the PVP coating would can retard the heat transfer from the shell. So the shell will first be converted to cobalt oxide, and the concentration gradient will drive the cobalt ions and oxalate ions in outwards, and finally form the hollow structure. This is called the surface locking effect. For comparison, we prepared the pure cobalt oxide without PVP coating. The TM images, as you can see, the undoped cobalt oxide is solid, while the doped one has a hollow structure, which is further verified by the ADS data profiler. In addition, in high resolution TM images, it shows interplanar distance of about 0.245 nanometer, corresponding to the 311 crystal surface. And through the refining of XRD pattern, we can find that carbon doping expands the crystal structure of the catalyst. And this hollow structure can provide large surface area for more efficient catalysis. To study the electronic structure and the carbon doping in the crystal, we provide some characterizations. First is the XPS spectrum, and after carbon doping, more cobalt ions with positive Q is observed to choose the carbon with positive for doping, and no typical peak corresponding to cobalt carbon here. It means carbon didn't replace the oxygen in the crystal. And the FTIR spectra shows two typical peaks at lower wave number, corresponding to the cobalt oxygen vibration, and the white peak at a higher wave number is attributed to the carbon oxygen carbon signals, and it means carbon is doping in the interstices of the crystal. We also investigate the deep band center of the materials, which is an important criteria to evaluate to affect their catalytic activity. And the pictures shows that after carbon doping, the deep band center shifts positively. It's close to the Fermi energy, and it means it has more unoccupied orbitals for stronger absorption ability for reactants. Based on this computation, we can find that carbon doping may enhance the can also enhance the conductivity of the materials, and the smaller radiance of the ES spectrum suggests that it may have a faster charge transfer kinetics. And the KBFM spectrum also shows a larger potential difference. It means during the electrolysis, it may have a stronger charge transfer efficiency. We first test their electrocatalytic performance for nitrate reduction, and from the LSV curves, we can find that after nitrate addition, both cobalt oxide and the doped one has a higher current density and more positive onset potential, indicating both materials are active for nitrate reduction. And after carbon doping, the doped one has a higher current density. We then employed two methods, the Indopheno blue method and the NMR method to determine the concentration of ammonia in the electrolytes, and also perform the control experiments to verify that the ammonia produced is produced from the nitrate reduction instead of the ammonia contamination from the environment. And after the calculation, and we finally obtained the ammonia yield rate and its physical efficiency. It's clear that the carbon doping can increase the ammonia yield rate and its physical efficiency at different potential, not only at the potential before negative 0.6. The physical efficiency is as high as nearly 100%, but after this potential, the Fe decreases due to the competing hydrogen evolution. And the obtained performance for ammonia synthesis is higher than most reported catalysts for ammonia synthesis by different nitrogen species reduction. Then we employed FTI spectra to investigate the mechanism of nitrogen reduction, and we observed the three important intermediates during the catalysis, and then based on the results, we performed calculation, and we found that the nitrate tend to bond with cobalt atoms through the nitrogen atom. It means cobalt may be the active site for the catalysis, and in the energy profilers, we found two important differences. First is that the carbon-doped cobalt oxide may have a stronger adsorption ability for nitrate ions, and the hydrogenation of nitrate intermediates may be the rate determining step. And obviously, the carbon doping may decrease the energy barrier of the RDS, and finally facilitates the whole catalysis process. Based on the outstanding catalytic activity of the carbon-doped cobalt oxides catalyst cathode, we then assembled a zinc nitrate battery. This is a schematic illustration with this catalyst as a cathode and the zinc as anode. During this battery, the nitrate can be steadily reduced to ammonium while generating electricity. And this battery shows open circuit voltage of 1.45 volts with a maximum power density of about 6 milliwatts per centimeter square, compared with the reported zinc and other zinc-based batteries via different nitrogen species reduction with different catalysts. We found that our zinc nitrate battery has a higher power density, and it can power an electronic timer for at least 1 day. While this battery can supply the electricity, it can also produce the ammonia as the cathode, and at different current discharge currents, it still shows high efficiency above 90% with good stability. So in conclusion, in recent years, many different zinc-based batteries have been reported for simultaneously pollutant converting to ammonia and electricity generation. So devoted in this direction, we have made some work and developed a carbon-doped cobalt oxide as efficient catalyst, and then assembled zinc nitride battery with high power density and high current efficiency for ammonia synthesis. Here I'd like to thank for the support from the fundings from fellows and the collaborators in the lab. Thank you for your time.